Okay, so now we're going to start with chapter 6, and we're going to pick up where we left off with the structure of the atom. We knew that the electrons are not in the nucleus, they are outside of the nucleus, and now we're going to talk more about how the electrons are organized. Okay, so we're going to start by talking about the nature of light. So, and eventually what we're going to do is we're going to sort of come back to the periodic table and see how it's organized and how everything is related to each other. So originally the periodic table just evolved because of experimental observations. People knew how things, how different chemicals acted, and they were kind of put together by similar properties. But there were a lot of elements missing, and so there needed to be more of an explanation about why the periodic table works. Why do elements in the same column exhibit similar properties? So before we can understand that, as I said, we need to talk about light. Okay, so light is a wave. Light actually oscillates in both the electric field and the magnetic field, but we're just worried about the wave itself. So, you know, we have a wave. A wave is a continuously repeating change or oscillation in matter. This is going up, down, up, down. The wave is kind of just the matter is actually just moving up and down. Kinetic energy is transferred through air while the air stays in place. So the energy is kind of, even if it's staying in place, it's going up and down, up and down. So light acts like a wave. Like I said, it has waves both in the electric field and the magnetic field. When we talk about light, we're not just talking about visible light, but we're including all the different types of light. So that can include X-rays, radio waves, ultraviolet, infrared, all of the forms of the electromagnetic radiation. So let's talk about a wave. A wave can be characterized by both its wavelength and its frequency, and then actually its amplitude also. So the wavelength, which is given the symbol lambda, it's the distance between any two adjacent identical points of a wave. So it's the length of one wave. And then the frequency, which is given the Greek symbol nu, which looks kind of like a cursive V, but it's called nu. Frequency is how many waves pass a fixed point per second. And then the amplitude is just kind of like the height of one of the humps. So it's actually 1/2 the distance between the peak and the trough. So how high up does it go, and then how low does it go? Okay, so let's look at this picture here. So if we look at this first one, we can say we have a wavelength. The length is just the distance from one point on one wave to the same point on the next wave. Of course, we could call that a wavelength as well. They should be the same, the wavelength. And then the frequency is how many waves do you have per unit time. So how many waves pass by in 1 second. In this case, you can see that the frequency is 3. You can say 3 per second, or sometimes we use the term hertz, which also means per second. If you look down here, we have the wavelength is shorter. So wavelength 2 is much shorter than wavelength 1, but notice that the frequency is higher. So this has 6 cycles per second. And if we shorten the wavelength even more, then we have even more cycles per second, or higher hertz. So what this tells us is that wavelength and frequency are inversely related. As the wavelength gets bigger, the frequency goes down. And we haven't talked about energy yet, but you can almost see that the energy of this is lower, whereas the energy of this is higher, because it's just got a higher frequency. So we'll look at that in a minute. Okay, the amplitude is just another measure, and the amplitude is half of the total distance from the top to the bottom. So if that's that's twice the amplitude, so the amplitude is half of that. So from the center up or from the center down. And you can see here that both of these have the same wavelength and they have the same frequency, but the second one has a lower amplitude. We're not going to be nearly as worried about amplitude as we are wavelength and frequency. All right, so because wavelength and frequency are inversely related, that means that their product is a constant. And it turns out that if you take frequency times wavelength, the constant that you get is, especially if it's in a vacuum, which of course is ideal, and not what we normally see. But anyway, we're going to use these values. The wavelength times the frequency equals c, which is the speed of light in a vacuum. And notice, so c is just a constant, 2.998 times 10 to the 8 meters per second. Notice that if you round it up to 3 sig figs, it's 3.00 times 10 to the 8th meters per second. And so you can see it takes in, the wavelength in terms of meters and the frequency in terms of per second. And so if you multiply them, you get the speed of light meters per second. So if you know the wavelength, you can find the frequency. If you know the I pointed to the wrong. If you know the wavelength, you can find the frequency. If you know the frequency, you can find the wavelength. All right, so let's do an example. A laser used for eye surgery produces radiation of lambda equals 640 nanometers. What is the frequency of this laser? So we know, I'm going to write it up here so it doesn't get in the way. We know that the wavelength equals lambda nu. So the frequency times the wavelength. So if we know the wavelength, we can find the frequency because we know what c is. But keep in mind that c, the units of c are meters per second. So that means when we're using this equation, we always have to put the wavelength in terms of meters and then the frequency in per second, which is the same as hertz. So the first thing we're going to have to do is convert 640 nanometers to meters. And there are 10 to the minus 9th meters in 1 nanometer. So if we have 640 nanometers, 640 times 10 to the minus 9th meters. So there's 10 to the minus 9th meters in 1 nanometer. Now, technically, this is not correct scientific notation. If you were to write it into correct scientific notation, it would be 6.4 times 10 to the minus 7th meters. However, because we're using it in an equation, it doesn't matter which one you use. They're both the same number. This one's technically not correct scientific notation, but it's probably the easiest one to use because we can remember the nanometers. All right, so we have our equation. So there we go. let me erase that so that it's not in the way. All right, so 640 times 10 to the minus 9 meters. Now we can plug it into our equation. Lambda nu equals c. So that means if we rearrange it, you can plug it in and then rearrange it, or you can rearrange it and then plug it in. Since we're looking for frequency, frequency will equal c over lambda. So that's what we have here. I guess I use this one, 3 times 10 to the 8th meters per second, because it only needs 3 sig figs, because this has 3 sig figs. And even that one's questionable, but we can go with 3. So 640 times 10 to the minus 9th meters, 3 times 10 to the 8th meters per second. Notice what happens, the meters will cancel. And so we have inverse seconds, which is the unit for frequency. So 4.69 times 10 to the 14th inverse seconds, or 4.69 times 10 to the 14 hertz. So it's a pretty straightforward problem. Again, hertz or per second, either one's fine. All right, and let's do another quick example. I think this is interesting because you don't really think about it, but an FM radio station broadcasts at a frequency of when say the call number is 103.4. What that means is it's got a frequency of 103.4 megahertz. So again, so now what's the wavelength? We know C equals nu lambda, or lambda nu. Again, the important thing is we have to make sure that our wavelength is in meters and our frequency is in hertz or inverse seconds. So the first thing we have to do here is convert 103.4 megahertz to hertz. So there's a 10 to the 6th hertz in 1 megahertz. So 103.4 megahertz is 103.4 times 10 to the 6th hertz. And then if we plug that into our equation, so lambda equals C over nu. This time, I guess, because there were 4 sig figs, I used 4 sig figs. 2.998 times 10 to the 8th meters per second divided by 103.4 times 10 to the 6th per second. Again, notice that the per seconds will cancel and our unit will be meters. 2.899 or about 2.9 meters. So I just want you to think about that for a second. 2.9 meters is pretty long. One wave is that long. It's kind of like it's like 3-meter sticks stuck together, and that's just one wave. Anyway, so in this case, we don't really need to convert to nanometers. Sometimes when we're dealing with small numbers, it's more helpful you could keep it in meters, no problem, or you can convert to nanometers, but this one is fine with meters. All right, so the range of frequencies or wavelengths then is called the electromagnetic spectrum. And so we'll take a look at that on the next slide. So visible light is only a very small portion of the electromagnetic spectrum. Visible light goes from about 400 nanometers to 800 nanometers. And so then we have other types of electromagnetic radiation beyond these wavelengths that are not visible to the human eye, but we know that they're out there. We can detect them. Okay, so here's what the electromagnetic spectrum looks like, and notice that visible light, of course, is just a very small portion of this whole spectrum. And if you look here we have wavelength. So this is, here's wavelength that's in the, greater than 1. So we see the TV frequency, TV radio waves are large wavelengths. And then we have 0.1, 0.01, 0.001. So we're in the millimeters, and then we're into the micrometers, and into the nanometers, and then down here into the picometers. Anyway, so you can see that the visible spectrum is in the about 400 to 800 nanometers. Just to the right of the visible spectrum is, just to the right of the red, is the infrared. And then the far infrared, near infrared, far infrared. Then we get into, of course, our microwaves, radar, and our TV and radio waves. So all of this, and notice here frequency. So what's happening? So the wavelengths are getting bigger to the right, very tiny, 10 to the minus 12 meters, nearly 1 meter. So the wavelength is getting bigger as you go to the right, and notice that the frequency is getting bigger as you go to the left. And as we said earlier, frequency and energy are actually related. We'll talk about that in just a second. So actually, our energy is also increasing as we go to the left. So energy increases, and frequency increases as we go to the left. Of course, sometimes you might see this in the other way. So it's not necessarily left or right, but as energy increases, frequency increases, and then we notice that the wavelength increase is going to the right. And so they're inversely related. Down here, left of visible, we have left of the violet is the ultraviolet, and ultraviolet, of course, has a higher frequency and a higher wavelength. Here's just another view of the electromagnetic spectrum. It's kind of a little more interesting to see here. Does it penetrate the Earth's atmosphere? Visible light does, infrared light does, radio waves do, but obviously not some of these others. And then you can, what this is showing you, so these are the wavelength in meters, so we know we got really tiny and then much bigger, 10 to the third, so sometimes up to 1,000 meters, which is as tall as a building. You can see microwaves are about as long as a human being, and or between a butterfly and a human being, and then infrared about the size of a needle point, and ultraviolet is about the size of a molecule. X-rays are about the size of an atom, and then gamma rays are about the size of a nucleus. So, and then down here you just see some of the uses that some of this electromagnetic radiation is used for. Anyway, it's just kind of interesting. All right, not all waves are traveling waves. There are such a thing as a standing wave or a stationary wave, and these are waves that are constrained. We're not going to be doing much with this, but it's kind of interesting to add a little bit. Standing waves also play an important role in understanding of the electronic structure of an atom or molecule. An example of a standing wave is a vibrating string, so like musical instruments and things. So that has a fixed point on two ends. That's an idea of a one-dimensional standing wave. So here you can see a vibrating spring shows this standing wave, and depending on how it fluctuates, you can have different waves. Just note that if you've got a point between these little points right here, these are called nodes. Okay, so up until about 1900, classical physics reigned supreme. Classical physics could explain pretty much everything that needed explaining up until that point. But as people started studying the atom and electrons and things like that, the classical physics started to have limitations, and the predictions didn't always carry through. And so the idea that there's more to the universe than what we can see started to be important. So Max Planck was one of the first scientists, and he solved what is called the ultraviolet catastrophe. And what is that? I think that's on the next slide. So certain objects are called black bodies. Black body radiation. Black body radiation emits radiation of all wavelengths. So the sun is an example of a black body. So if we look at the distribution of solar radiation, and this is wavelength in nanometers, so where's our visible light is right here between about 400 and 600. So this is visible light, and you can see that most of the radiation coming from the sun is in the visible spectrum. There's a little bit in the ultraviolet down here, and then there's some that's at higher wavelengths also. There's also light in the UV, in the IR portion of the spectrum. If you have a hot piece of metal that is glowing, that's also a black body and also shows the same distribution. So you can see that the blue line is the black body spectrum of a really hot metal, and the orange is the spectrum of sunlight. And so one thing that's important to note is that this distribution depends only on the temperature of the metal, and it didn't matter what the metal was, but when it got to 5,250 degrees Celsius, it showed this spectrum. So what this chart is showing us, that if you have different metals or different if you increase the temperature of a black body, so here you got 2500 K, 3400 K, 44, 5500. Notice that what's happening is that there is a shift into the visible light. So as you know, the maximum here, the maximum wavelength at 2500 is up here around 1400 nanometers. And at 3400 it shifts, the maximum shifts. At 4400 it shifts again. It's just starting to get into the visible wavelength. And then if the temperature at 5500, notice that it's at maximum in the center of the visible, and so it's got a lot of the visible spectrum. This is why hot objects appear to glow, because they start to have this visible wavelength. Just interesting, the human body at 310K emits 0 visible light, so that's why when the lights go out, we're not glowing. we can't see other people. Okay, so what's interesting is that classical physics, classical electromagnetism that was known at the time could not account for this shift in wavelength. If you had math models at the time, they did not predict that the intensity would dip down to the left. So, you know, here we had this. So the model said that the intensity was just going to keep going up and up and up and up, and instead it comes back down in the ultraviolet area. This was the ultraviolet area. This is from the previous slide. So classical theory predicted that intensity would just keep going up infinitely as wavelength decreased. So as wavelength got closer to 0, intensity should be nearly infinity. But of course that's not doesn't happen. We see this decrease back again in intensity on the left-hand side of the peak in the ultraviolet area. So if it kept going infinitely, this would imply that every time we use the oven, we would get blasted with UV radiation, which of course is not true. But anyway, this was dubbed the ultraviolet catastrophe because math models predicted that it would go up and up and up instead of come back down in the ultraviolet. And so obviously they knew that the math models of the day didn't explain light and wavelength, and or at least particles with wavelengths at this size.